Hi students, in this chapter we are going to learn about a lot of common compounds that we use in our daily life. We're also going to learn about some uncommon compounds which are important but which we don't use in our daily life. For example, we are going to learn about cement, we are going to learn about paints, we are going to learn about paper, gunpowder and many other interesting chemical compounds. So let's proceed and understand how some chemical compounds are manufactured, what's their use, etc. Let's start off with a very common substance that we use in our daily life, cement. So what exactly is cement in the first place? Cement is a binder. It is a substance that is used to bind other materials together because of its property to harden as time passes. So as you may already know, cement basically binds two substances together, and such a substance is called a binder. Now the exclusive property of cement that makes it so very useful is that a certain mixture of cement and water is very soft initially when you apply it between two surfaces, but as time passes the mixture hardens, and therefore as cement hardens, the two substances in between which cement has been applied they get joined together. So that is how cement works. The common cement that we use in our daily life is called Portland cement. Let's understand the process of production of Portland cement. Portland cement is primarily produced by heating a mixture of calcium carbonate and clay to a temperature of around 1450 degrees Celsius. Some other substances are also added to this mixture, but the primary composition is that of calcium carbonate and clay. Now when you heat calcium carbonate, what do you get? On heating, calcium carbonate decomposes to produce oxide and carbon dioxide. That is shown by this equation here. In fact, this reaction is also called a calcination reaction. You see, calcium carbonate and clay are heated in the absence of oxygen. Any reaction which takes place in the absence of oxygen and involves the decomposition of a substance is called calcination. So calcium oxide is produced after calcination because carbon dioxide escapes into the atmosphere. The mixture of calcium oxide and clay that remains once the initial mixture is heated is called clinker. At this point, some gypsum, that is calcium sulfate .2H2O, is added to the clinker, and this mixture of clinker and gypsum is basically called ordinary Portland cement. It is the simplest form of cement, you can say. Calcium oxide, clay and gypsum, mix all of these up and you get ordinary cement. Of course, in reality, a lot of other sophisticated chemicals are also added to produce the best quality of cement. These are some of the chemicals which are added along with calcium carbonate and clay to produce the best quality cement. So for example, tricalcium silicate is added, dicalcium silicate is also added, gypsum, as we saw, is definitely added. So you can look at these substances. They are also present in cement. Now in general, when we make use of cement in our daily life, we don't use cement directly. For example, cement is not directly used to build all our houses. Cement is first converted to something called concrete, and it is this concrete that is used to build bridges, that is used to build houses, that is used to build all kinds of structures, roads, etc. So what exactly is concrete? I'm sure you must have heard of the term. Concrete is a mixture of cement, some substances called aggregates, basically gravel and sand. Small stones or small rocks are called gravel. So concrete is a mixture of cement, aggregates and water. When you mix cement, aggregates and water, the mixture on hardening becomes so strong that it's used to build bridges and houses. There you go. This is how you get concrete. Understood? Note that if you just mix cement and water, even then the mixture will harden after some time and it will help join two substances together. But if you also add in these aggregates, gravel and sand, then the strength of the mixture will further increase, and that is the reason aggregates are added to this mixture. Understood? The wonderful advantage of concrete is that it keeps getting harder and harder over time, and so the houses built using concrete, they keep becoming stronger and stronger over time, and that's amazing. There's another mixture of cement, water and sand that is called mortar. The only difference between concrete and mortar is that mortar is not as strong as concrete, so it is used for purposes where that much strength is not required. For example, mortar is used, if there is some crack in some wall of your house, so mortar is used in cementing that crack. Or let's say you have to build some roads, mortar is used in building certain kinds of roads, or certain walls. So mortar is used where a lot of strength is not required. The difference between mortar and concrete is that it doesn't have gravel in it. Cement, sand and water forms mortar. With respect to concrete, how much cement must be mixed with how much amount of aggregates and how much water? Well, it has been found that the perfect composition to form, strong concrete is that to produce 1 meter cube of concrete, you take 300 kg of cement and you take 160 liters of water and you take some aggregates. When you do that, you get 1 meter cube of concrete. So there you go. That's about cement. Until now we talked about what cement consists of, how cement and water and aggregates can be mixed to form concrete. But how does cement really work? What happens is that generally you take a mixture of cement, water and aggregates and you apply it between two substances. When you allow this mixture of cement, water and aggregates to dry, that water is absorbed by the substances inside the cement, and this hardens the substances inside the cement. Understood? A lot of hydration reactions occur. Hydration means addition of a water molecule to any substance. That is what hydration is. So when you add water to cement, the water bonds with the different compounds present inside cement to form hydrated compounds, and these compounds are very, very hard, much harder than the original cement. And so after some time the cement and water mixture becomes very hard, and that gets attached to both the substances. This hard substance that is formed gets attached to both the substances that the cement is supposed to join, and the two substances get joined. Understood? This hardening of cement when water is added to it is called the curing of cement or setting of cement. So you must remember this fact: curing or setting of cement. So that was about cement, a common mixture that we see in our daily life. Another very common mixture is ink. Of course, you must have used ink at some time or the other, right, to write on your papers. What exactly is ink? Also, how is ink prepared? What does it consist of? Let's find that out now. So what is ink? Ink is basically a liquid or a paste that contains pigments or dyes, and the purpose of ink is to color a surface to produce an image, text or a design. So basically, what is ink? Ink is just a liquid or a paste that contains some pigments. Understood? These pigments are coloring agents that impart color to the ink, and as we already know, it is used to write, or produce image or text. So let us go deeper and try to understand exactly what ink consists of. We'll study printing inks in this chapter. We'll not study writing inks because they are not that important. Now, any printing ink basically consists of three components. The first one is called colorant, the second is vehicle, and the third is additives. What is colorant? Colorant is, that component of ink which imparts to it its color. There is black ink, blue ink, red ink, yellow ink. All these colors come from different colorants which are present in the ink. Understood? There are two types of colorants, pigments and dyes. Generally, pigments are preferred over dyes because of many different properties. Pigments have some properties which are much better than dyes, so they are preferred. There are many types of pigments. Pigments can be organic pigments, that is, pigments which are basically carbon compounds. Yellow lake is the example of an organic nitrogen based pigment. It is yellow in color, so it's used to impart yellow color to ink. Yet another famous pigment is chrome green. It is an inorganic pigment because it basically has chromium in it. So you can clearly see pigments can be organic or inorganic. Another popular pigment that imparts white color to ink is titanium oxide. So this compound will definitely be present in the ink which is used to print on black paper. Let's say you have to use white ink to print on black paper, then you must use titanium oxide. So these are the different types of colorants. What about vehicle? Well, the colorant must be suspended in some medium, right? You can't just have only the colorant. The vehicle is that liquid, which contains the colorant. It is that substance which takes the colorant and puts it on the paper. It's a liquid which transports the colorant onto the paper. Understood? In many inks, the vehicle sometimes dries off after you've printed, so that the colorant gets stuck to the paper and the vehicle dries off. Two very common vehicles are linseed oil and soybean oil. So you can see that generally oils are used as vehicles. The third component of all inks is additives. Additives are substances which are added to the ink to improve the properties of the ink. For example, there's a compound called monothanomaline. This is added to the ink to increase the viscosity of the ink when you want to make the ink thicker. Then there is wax, our very own wax, candle wax. A small quantity of it is added to the ink to remove certain printing defects. Then eugenol is a compound that is added to ink because of its antioxidant properties. So it prevents the ink from getting excessively oxidized. So you must understand that these are some kinds of additives and basically they improve the properties of the ink. So these are the three substances which any ink consists of: a colorant, vehicle and additives. Now we just talked about the composition of inks, but how are inks prepared? The preparation of ink basically involves two processes. The first process is called varnish manufacture. The second process is called dispersion of pigments in varnish. Varnish is basically a mixture of the vehicle and the additives. Understood? So vehicle plus additives equal to varnish. The first process is mixing the vehicle and the additives, and the second process is dispersing the pigments in a mixture consisting of vehicle and additives. This figure you see on your screen shows the process of the preparation of varnish. Now I know the process seems very complicated, but don't worry, you needn't remember the entire process, as you will just be asked objective type questions in NDA. Just remember that the crux of this process is that additives and the vehicle are mixed together. You can see a blue tank here. The additives and the vehicle are mixed together in this blue tank. The rest of the process is just shown for your information. It's okay if you don't get into the details of this process. As I said, the second part of the process of preparing ink involves dispersing the pigment in the varnish. Dispersion basically means that you sort of dissolve the pigment particles inside the varnish. The pigment particles don't exactly dissolve, but they spread out inside the varnish, that is the additive and vehicle mixture, and this process is called dispersion. Spreading out is called dispersion. And the pigment is ground into very very small particles, and these particles are dispersed inside the varnish. To grind the pigment, we generally use three types of equipment. We use a 3-roll mill, or sometimes we use a bead mill, and sometimes we use a cavitation mixture. In this animation that you're seeing on your screen, a 3-roll mill is shown. So a 3-roll mill, basically takes in pigment particles, and 2 rolls grind the pigment particles to form very tiny particles, and these particles are then dispersed inside the varnish. Understood? So the main part of this second process is breaking the pigment particles down into very small particles so that they can easily get dispersed inside the varnish. There you go. So that was the process of preparation of ink. Now that we've learnt about cement and ink, let's solve a small example related to cement and ink. Which of the following is not an important component of ink? A. Vehicle, B. Absorbent, C. Colorant, or D. Additive? Well, the answer is quite clear. We just learned that every ink consists of a vehicle, a colorant, and an additive. So the only substance that is not a part of ink is adsorbent. There you go. That's our answer. Let's now move on and study yet another very important substance that we use in our daily life: glass. So what exactly is glass? Glass is basically used to refer to all substances which are amorphous, transparent, and brittle. An amorphous substance is a substance which does not have a fixed crystal structure, a regular crystal structure. There are amorphous solids and crystalline solids. In crystalline solids, at the microscopic level, the substance consists of a definite fixed arrangement of crystals. There are cubes and cubes and cubes placed one after the other in a regular arrangement, or there are some other types of crystals placed one after the other in a regular arrangement. Sodium chloride or common salt is a crystalline substance. Glass is an amorphous substance. This means that there is no regular arrangement particles that make up glass inside it. Understood? In fact, any amorphous, transparent, and brittle substance is called glass. A brittle substance is a substance that breaks easily when you hit it with a hammer. And of course, we all know that glass breaks easily. There are generally two types of ordinary glass that we use in our daily life. There are many types of glass, and we'll even study about them, but the two types that are very, very common are container glass and window glass. Container glass is the glass used to make containers of glass, like your glass plates, the glass that is used in making chemical containers used in chemistry labs. That's container glass. And window glass is used to make windows. Both of these types of glass are also called soda lime glass. Understood? So ordinary glass is soda lime glass. As you can see, this is the chemical composition of ordinary glass. The primary percentage is that of silicon dioxide. Container glass and window glass both contain more than 70% silicon dioxide. Silicon dioxide is actually sand, The sand or mud that we see in our daily life is silicon dioxide. However, in glass it is present in a very special form called quartz. Understood? Sodium oxide, Na2O, is also present in a good amount in container glass and window glass, 13% and 14%. Then there's calcium oxide also, 10% and 9%. So these are the major constituents of the ordinary soda lime glass that we use in our daily life. There are of course other types of glasses too. For example, there is fused silica glass. This glass has a very, very high percentage of silica, and it is also very chemical resistant. This means that it doesn't react no matter what chemicals you add to it. It's very difficult to make this kind of glass react. So it can be used to store very, very reactive chemicals. Another advantage of this glass is that it can be heated to 1500 degrees Celsius. Understood? So definitely it is heat resistant also. That's fused silica glass for you. Then we have soda lime glass, which we just discussed, the ordinary window and container glass. Then there is Pyrex glass. Pyrex glass is a special type of glass that has a very high content of boric oxide in it. It is generally used in the manufacture of car lamps. Understood? Another type of glass is crystal glass. The special property of crystal glass is that it has a very high refractive index. Now that means that when light passes through crystal glass, it undergoes so many refractions that you see a very brilliant arrangement of crystal glass. So you must have seen precious crystals made of glass. They must be made of crystal glass. Crystal glass has a large composition of lead oxide and zinc oxide in it. Then there is aluminosilicate glass. This type of glass has boric oxide, barium oxide and magnesia in it. Magnesia is nothing but magnesium oxide. Aluminosilicate glass is the glass that is used in glass reinforced plastics. So this glass is famous for its strength. It is also used in the making of halogen lamps. Halogen lamps are lamps which contain a halogen like chlorine or fluorine, and they glow really brightly. So aluminosilicate glass is a special type of glass that is used in the manufacture of halogen lamps and in the manufacture of glass reinforced plastics, which is also used to make chairs. Another type of glass is oxide glass. Oxide glass contains 90% aluminium oxide and 10% germanium oxide. Oxide glass is used to make fiber optic cables. You must have heard of this new technology called fiber optic technology. It involves the transfer of light from one place to another by means of a phenomenon called total internal reflection. Light inside fiber optic cables keeps getting reflected here, there, and it moves forward. So oxide glass is used in the manufacture of fiber optic cables. So you can see these were the different types of glass. Understood? Yes, you must remember all these types. So types of glass is okay, but how exactly is glass prepared? Well, the crux of the process is quite simple. As you can see, different types of glass consists of different types of substances. In every case, all the components of glass are powdered first, they are broken down into small particles and then they are mixed. The mixture is then heated for around 5 hours at a temperature of around 1600 degrees Celsius. When that is done, glass is produced. Once glass is produced, it is converted into the appropriate shape using two techniques, either the blow and blow technique or the push and blow technique. In the olden days, what used to happen was that once liquid glass was produced, molten glass, then people used to blow air into the glass to give it the proper shape. These days machines are used to give proper shape to the glass, and the techniques these machines use is the blow and blow technique or the push and blow technique. So there is not much to glass manufacture. All the components are mixed and then blow and blow or push and blow is used to give shape to the glass. Here's an example that will help you better understand glass. Can you tell me which of the following types of glass contains germanium oxide? Is it oxide glass, sodium borosilicate glass, soda lime glass, or fused silica glass? Well, again, the answer is oxide glass. As I had just told you, oxide glass contains 10% germanium oxide and 90% aluminium oxide, and it is used in the preparation of fiber optic cables. The next substance we will learn about is gunpowder. Gunpowder is an explosive. Have you heard of it before? It is used to blast mines, and in the olden days, in the 19th century and the 18th century, it was a very powerful explosive that was used in wars. What exactly is gunpowder? What does it consist of, and how can it be prepared? Let's find out. Gunpowder basically consists of three substances. It has sulfur, that's 16% of gunpowder, charcoal, that's 14%, and then it has potassium nitrate, KNO3, 70%. These are approximate compositions of gunpowder. The composition of sulfur, charcoal and potassium nitrate varies. depending on the type of gunpowder. However, these are the three substances that make up gunpowder, that is for sure. The purpose of sulfur is that it serves as a fuel. Some fuel must burn, right, if an explosion has to occur. It also lowers the ignition temperature of gunpowder. Charcoal, again, it also works as a fuel. Potassium nitrate provides oxygen to gunpowder. You see, the formula of potassium nitrate is KNO3. So there are 3 molecules of oxygen in potassium nitrate, and that oxygen is required for burning. So potassium nitrate provides oxygen for burning. So you must remember the composition of gunpowder: sulfur, carbon and potassium nitrate. This is the reaction that occurs when gunpowder explodes. So you can see that KNO3, potassium nitrate, reacts with sulfur and carbon to form potassium sulfide, K2S, nitrogen gas, N2, and carbon dioxide gas, CO2. Understood? So this is the chemical reaction of the burning of gunpowder. When 1 kg of gunpowder explodes, that produces 3 megajoules of energy. That's quite a lot of energy. Of course, modern day explosives produce much more energy than this. That is why these days gunpowder is not used in wars or as an explosive device. It is used basically to help in mining and other industries. Understood? Because its explosive power, the energy it releases, is much less than that of modern day explosives, but it is enough to blast off mines. So how is gunpowder basically prepared? Well, gunpowder is really prepared by means of a very simple process. After all, gunpowder just consists of 3 ingredients, isn't it? So all these 3 ingredients are mixed together, some water is added to them, and they are stirred. And there you go, gunpowder is ready. This figure you see on your screen shows an olden day equipment to prepare gunpowder. These wheels would rotate and they would crush all the ingredients, and then the ingredients would get mixed up. Water would be added at the beginning because the presence of water would prevent these substances which were mixed to make gunpowder from exploding right away. So water would be added to lessen the impact of the gunpowder, and to lessen the risk of it exploding. So that's the simple preparation of gunpowder. Here's an example that can shed more light on gunpowder. Which of the following statements is wrong? KNO3 supplies oxygen in gunpowder. Sulfur serves as a fuel in gunpowder. Sulfur lowers the ignition temperature. Carbon serves as a fuel and lowers the ignition temperature. Well, can you guess the right answer? The right answer is option D. After all, we are being asked which of the following statements is wrong, and you can see that statements A, B and C are correct. Potassium nitrate does indeed supply oxygen in gunpowder. Sulfur does indeed serve as a fuel in gunpowder. Sulfur also lowers the ignition temperature. Carbon serves as a fuel, but it does not lower the ignition temperature of gunpowder. When I say lowering the ignition temperature, I mean lowering the temperature at which gunpowder explodes. So carbon does not lower it, sulfur lowers it. Therefore, option D is the statement that is wrong, and so for us it is the correct option. So that was about gunpowder. The next substance we will study about is safety matches. I am sure you must have used safety matches in your daily life, isn't it? You just strike a match against the matchbox and there you go, you get a ready source of fire. So what do safety matches really consist of? What are the substances that make up safety matches? And how are safety matches prepared? Now, one amazing thing that you must understand about safety matches is that safety matches require both the match and the matchbox to light up. That is the reason they are called safety matches. Understood? You see, in the olden days, when the first matches were produced, they would light up when you struck the match against any rough surface. But that was dangerous, you see. You might accidentally strike a match against a rough surface and you would get fire. Safety matches are very safe because they will produce fire only if the matches strike the matchbox. You can strike the matches against any surface and you will not get fire. You can strike the matchbox against any surface and you will still not get fire. You have to strike the matchstick against the matchbox. So that is why safety matches are basically called safety matches. First, here are the ingredients present in the match. The match contains 45 to 55% potassium chlorate. Potassium chlorate provides oxygen for the burning of the match. A little sulfur is present. Sulfur is the fuel that burns in the match. A neutralizer is present, like zinc oxide or calcium carbonate. This neutralizer helps in controlling the reaction, to make sure that the reaction doesn't get out of control. And 20 to 40% substances like filler and glue are present. They basically help, bind the chemicals in safety matches together and to fill up space. What about the matchbox? The matchbox contains 25% powdered glass. Of course, you need friction to strike a fire, right? So powdered glass provides friction to the matchbox. 50% red phosphorus is present. Red phosphorus is a very inflammable substance. It burns very well as a fuel, so it is present as a fuel. 5% of a substance called neutralizer is present, again to control the reaction. 4% carbon is present and 16% of a substance called binder is present to bind the chemicals together. So we can see that different chemicals are present in the match and different chemicals are present in the matchbox. When you strike the matchstick to the matchbox, all these chemicals combine together and a fire is produced. Note that all the chemicals are required to produce fire. As I said earlier, you cannot produce a fire only using a matchbox or only using a matchstick. Understood? So how are safety matches manufactured? Well, the process is quite simple. First of all, wood is cut in the shape of matchsticks. After all, matchsticks are made up of wood. Then, this wood is placed in the holes of a certain belt. These wooden sticks are placed in the holes of a certain belt. So you take a lot of matchsticks and place them in the holes of a certain belt. The belt keeps on moving. Now as the belt moves, it dips these sticks in certain chemicals, present in tanks. And these chemicals present in chemical tanks, they stick to the surface of the matchsticks. And therefore, when these chemicals dry off, our matchsticks are produced. Understood? This is how matchsticks are manufactured. There you go. That's the basic process. Let's answer a question to further understand safety matches better. What are the chemicals present in safety matches? Red phosphorus, white phosphorus, yellow phosphorus, or potassium nitrate? So, do you know the correct answer? Well, the correct answer is definitely red phosphorus. Red phosphorus is present in the matchbox, that is a part of the safety match system. White phosphorus is indeed another type of phosphorus, but it is not present in matches. Yellow phosphorus doesn't exist, and potassium nitrate is not present. Note that potassium chlorate is present, but that was not given in any of the options. So we have to go with red phosphorus. Let's now move on to the next substance that we will study. Paints. Of course, you must have also used paints in your daily life. All of us must have painted as children, right? So what exactly is paint? Paint is any liquid composition which after application to a substrate gets converted into a solid film. That's a very good definition of a paint. You see, what this means is that paint is any liquidy substance which is initially a liquid, but once you apply it to a substrate, the substance you apply paint on, like paper or wood, or a canvas, once you apply it, that liquid dries off and it gets converted into a solid film. That's the crux of any paint. Now the question is, what does any paint consist of? All paints consist of 4 substances: binder, solvent, pigment, and additives. These are the 4 substances that are present in every form of paint. So let's see what each of these substances do. The binder does what its name suggests. It sticks the paint to the piece of paper or the canvas or the substrate on which the paint is being applied. So it just binds the paint to wherever the paint is being applied. The solvent, on the other hand, dissolves the different components present in paint, like the binder, the pigment, the additives. The solvent holds all of these. It's a liquid which contains all of the other components of the paint. The pigment is the color of the paint. Paint can be of red color, blue color, yellow color, any color, and that color is provided by the pigment. Additives are substances which are added to the paint to improve its properties. So for example, there are additives which improve the surface tension of paint. Some additives make the paint flow. Some additives make the paint flow less. Some additives prevent foaming of the paint. Sometimes foam can form while you're painting. So additives help in what the paint is doing. They are extra substances added to improve the properties of the paint. So these are the 4 main components that all paints contain. So how are paints prepared? Again, the process is quite simple. First of all the substances which are required to form the paint are mixed together. So the pigment, the solvent, the additives and the binder, all of them are mixed together. Now after the mixture has been formed, then this mixture is agitated along with sand particles. Now the additives, the binder and the solvent are not really affected when you agitate this mixture with sand particles, but the pigment gets ground and it breaks down into very tiny particles. Understood? So the pigment does indeed get affected when it is agitated with sand particles. Now this whole mixture, after being agitated with small particles and after the pigment has been broken down into smaller particles, is now agitated with solvent in proper amount. You see, the pigment consists of large particles. That is why we agitated this mixture to break the pigment down into smaller particles. Now this mixture, the water content in it must be increased or decreased depending on the use of our paint. So different amounts of solvent are added to the paint to make sure that it has the appropriate water content. So the paste is agitated with the proper solvent amount, and there you go, our paint is ready. So these are the 3 simple steps in manufacturing paints. Here's a question that will further clarify your concepts. What is the most essential component of paints? Binder, pigment, additives or oxidant? Well, we clearly have only 3 options and not 4 options, because there is nothing called an oxidant in paints. So it's either binder, pigment or additives. Now you see, without the pigment the paint can still technically exist. You see, after all, you may not have a color, but you can apply something, maybe something colorless, maybe something white, maybe something naturally brown onto the piece of paper. So even without a pigment you can apply paint to paper, isn't it? Additives, well, they are definitely bonus elements, but even without additives you can have paints. Without a binder there is absolutely no possibility of having paints. That's because the binder binds the paint to the paper or to the canvas. If there is no binder, the paint will flow off, isn't it? And there will be no painting. So the binder is the most essential of all components of paints. Understood? So this is important and you must remember it. Let's move on. Paper. Again, paper is also a very common substance that we use in our daily life. In this figure on your screen, you see the fibers that are present inside a sheet of paper. What does paper consist of? Did you know that paper actually contains water? Well, it does. So paper contains water. It contains substances called fillers, which fill up the spaces inside paper and also strengthen the paper. Paper contains some special substances called retention aids. Then it has some dyes which impart color to the paper. It has sizing agents which change the water retention properties of the paper. How will the paper behave when water is added to it? Will the paper get destroyed or will it be okay with water being added? Sizing agents determine that. And of course, paper also has fibers, wood fibers in general, which make up the bulk of the paper. As you already know, paper is made up of wood fibers, and it is these fibers which have been seen through a microscope in this picture. There are different types of paper, of course, and different types of papers have different substances in them. There is printing paper, which, as you know, is used for printing purposes. There is wrapping paper, the gift paper that you use. There is writing paper, blank paper, A4 sized paper on which you write. There is drawing paper, chart paper on which drawings and paintings can be made. There is blotting paper, which absorbs ink, extra ink. There is handmade paper, which can be used for many purposes, which is not made using paper machines, but which is manufactured by the hands of workers. So these are the types of paper. So how exactly is paper manufactured? Well, these are the main processes involved in paper manufacture: pulping, bleaching and paper making. You see, what happens is that first of all we have a tree, right? So once the tree has been cut, logs are obtained, wooden logs, isn't it? Now these wooden logs are then further cut and broken down to produce wood chips. Understood? Wood chips are very tiny pieces of wood. Now these wood chips are then placed in a machine or a container called a digester. In this digester they are cooked for some time, a couple of hours. When I say cooked, what I mean is that these wood chips are heated in the presence of two main chemicals, sodium carbonate and sodium hydroxide. Understood? The mixture of sodium carbonate and sodium hydroxide is called white liquor. So wood chips are heated in the presence of white liquor and some other substances for quite some time. That basically forms a paste of the wood chips. Understood? Wood chips basically contain a substance called lignin. That's the brown part of the wood, and it is this lignin which is not required in paper. You see, wood chips have lignin and they have fibers. Fibers are required for paper making and lignin is not required for paper making. So pulping crushes the wood chips, it forms a paste of the wood chips and also removes some of the lignin present in the wood chips. Understood? So basically the pulp produced from the digester, the substance in which all this cooking takes place, is light brown in color and it is like a paste. The lignin that still remains in this paste is removed by the process of bleaching. Bleaching is basically done using chemicals like chlorine, ozone, chemicals like that. In the olden days, the COH process of bleaching was used. These days, however, new techniques involving ozone are used. The COH process that was used earlier used chlorine, but these days ozone bleaching is being preferred because it does not pollute the environment as much as chlorine does. In fact, many countries have adopted total chlorine free bleaching or TCF bleaching, and some countries have adopted elemental chlorine free bleaching or ECF bleaching. So these are environment friendly bleaching methods. Bleaching basically means removing any lignin that is left in the pulp. That's what bleaching is. And of course, since lignin gives wood its brown color, after bleaching the pulp becomes white from brown. This white pulp, many chemicals are added to this white pulp like fillers, sizing agents, retention aids, the chemicals I just talked about, and then this white pulp is passed through a paper machine. When that is done, the paper machine rolls over the pulp and rolls on to form a thin paper sheet out of the pulp. So the paper sheet comes out of the paper machine. That is how paper is prepared. Of course, as you might have seen, is a slightly complicated process. But well, paper is important and we all use a lot of paper in our daily life. Here's a simple question regarding paper manufacturing. What is the substance that replaces chlorine in environment-friendly bleaching? Sodium hydroxide, sodium hypochlorite, ozone or sodium carbonate? Well, as I just told you, ozone is the substance that replaces chlorine in environment-friendly bleaching. These were the different substances that we have studied so far in this chapter. Let us now move on and study some processes that are important in your NDA examination. The processes to prepare sulfuric acid, the process to prepare nitric acid, and other important chemicals used in the industry. Let's start off with Nelson's cell, which is used to prepare sodium hydroxide in the industry. So as I just said, the first process that we will learn is the process of preparation of sodium hydroxide using a Nelson's cell. A Nelson's cell is shown in the animation that you are seeing on your screen. It uses sodium chloride and water to produce sodium hydroxide. So what happens in a Nelson's cell? Well, the arrangement shown on your screen looks quite complicated. But what actually happens is that there is a U-shaped container. You can see that here. The U-shaped container has a lining of asbestos, at its periphery, at its edges. Understood? So this grayish portion here is asbestos. The asbestos is further lined with steel mesh. Now what happens here is that we fill sodium chloride solution inside this U-shaped container. Understood? Then we electrolyze this solution. Electrolysis means that you pass electricity through a solution with the intention of splitting up the components of the solution into its constituent ions. So in this case, we fill this U-shaped container with sodium chloride solution. We place a black carbon anode in the middle of this U-shaped container. As you can see, this is the carbon anode. In any electrolysis process, the anode is the positive electrode and the cathode is the negative electrode. So basically we have a carbon positive electrode in the middle of this U-shaped solution. The outside portion of the U-shaped container is the cathode. So now we pass electricity through this sodium chloride solution. As you can see, sodium chloride solution is continuously coming into the U-shaped container here. Now when we pass electricity, sodium chloride splits up into sodium ion and chlorine ion, isn't it? But there is water also in the solution. So water splits up to form hydrogen ion and hydroxyl ion, that is OH minus and H plus, while sodium chloride splits up to form Na plus and Cl minus. In any electrolysis reaction, the positive ions move towards the negative electrodes where they gain electrons, and the negative ions move towards the positive electrode where they lose electrons. The sodium ions move towards the cathode and the chloride ions move towards the anode. According to the preferential discharge of ions, based on the electrochemical series, hydrogen ions are preferentially discharged at the cathode, while chloride ions are preferentially discharged at the anode. So hydrogen ions gain electrons to form hydrogen gas, while chloride ions lose electrons to form chlorine gas. Sodium ions and hydroxyl ions, Na plus and OH minus, are left inside the solution, isn't it? After all, they are not discharged at the anode or the cathode, and therefore this sodium hydroxide is formed inside the U-shaped vessel. As I said, the asbestos lining of the vessel is porous, so sodium hydroxide drips out through the porous asbestos lining and it falls down into this large rectangular container, and therefore sodium hydroxide can be collected and removed from the bottom of the container. As you can see, some steam is also pushed inside this container to make sure that the appropriate concentration of sodium hydroxide is obtained. So this is what happens in a Nelson's cell. Basically, there's sodium chloride solution, it is electrolyzed, current is passed through it, sodium ions and chloride ions are produced, hydrogen ions and OH minus ions are produced. Preferentially, hydrogen and chloride ions are discharged, so hydrogen and chlorine gases are released, while sodium ions and hydroxyl ions remain in solution. They come down to form sodium hydroxide. That's the basis of the Nelson cell. Here are the basic equations, at the anode and the cathode in the Nelson cell. As I had just told you, At the anode, the chloride ions lose electrons to form chlorine gas, and at the cathode, hydrogen ions gain electrons to form hydrogen gas. However, the equation is generally written like this: 2H2O plus 2E gives H2 plus 2OH minus. This is just a way to write the equation properly, but in reality hydrogen ions do gain electrons to form hydrogen gas. Here's an example based on the Nelson cell. Which of the following substances is produced at the cathode of a Nelson cell? A greenish yellow gas, a colorless gas that burns with a pop sound, sodium, or a brown gas? Now we already know that chlorine gas is produced at the anode of a Nelson cell and hydrogen gas is produced at the cathode of a Nelson cell. As you know, the cathode is the negative electrode and anode is the positive electrode. Now hydrogen gas always burns with a pop sound. That's its characteristic property. Therefore, our answer is this one. A colorless gas that burns with a pop sound is produced at the cathode of the Nelson cell. So that was about the Nelson cell. Let's move on to the next process called the Haber's process. The Haber's process is used for the production of ammonia from nitrogen and hydrogen gases. Let's see what happens in the Haber process. The animation that you see on your screen represents the Haber process. As you can see, what happens in the Haber process is that nitrogen combines with hydrogen to form ammonia gas. The Haber's process is the process for the preparation of ammonia. In the Haber's process, nitrogen and hydrogen first enter a chamber called the reactor. This is the reactor in the middle. Nitrogen and hydrogen enter in the proportion 1:3. That is, the amount of hydrogen entering the reaction chamber is 3 times the amount of nitrogen entering the reaction chamber. This is done, in the proportion in which these gases react. The gases are sent in the proportion in which they react. Inside the reaction chamber, the conditions are pretty intense. The temperature is around 400 to 450 degrees Celsius and the pressure is around 200 atmospheres. That's really high pressure, considering the fact that the general pressure we have on Earth is 1 atmosphere. An iron catalyst is also used in this reaction. So without an iron catalyst, the reaction won't occur. So under these conditions, nitrogen combines with hydrogen to form NH3, that is ammonia gas. So ammonia gas is now allowed to pass through another chamber. In this chamber, a coolant, a liquid which absorbs heat, is circulated. So these zigzag wires that you see, these zigzag pipes, they are basically circulating a coolant, a liquid that absorbs heat. So this liquid absorbs heat from ammonia gas and condenses it. It condenses ammonia gas to ammonia liquid. Ammonia liquid drips and it can be easily collected here. Some nitrogen and hydrogen may be left unreacted, despite passing through those stringent reaction conditions. This unreacted nitrogen and hydrogen is passed from this second reaction chamber back to the initial reaction chamber. Understood? So they are reused, and that's it. This is the simple preparation of ammonia using the Haber's process. So basically all you have to remember is that nitrogen and hydrogen are in the ratio 1:3. An iron catalyst is used. The temperature is 400 to 450 degrees Celsius and the pressure is 200 atmosphere. So that was the Haber's process. Here's a question about the Haber's process. So here's your question. Which of the following catalysts is used in the Haber's process? Iron, copper, platinum or rhodium? Well, clearly the answer is iron. We just talked about it, isn't it? So such questions may be asked in the MDA examination. Do note that you can always visit TopCoaching.com for more information related to all of these topics. Let's now move on to the next process, the lead chamber process for the preparation of sulfuric acid. So let's start off with the lead chamber process. So what exactly is happening in the lead chamber process? The lead chamber process is the process that was used earlier in the manufacture of sulfuric acid. It was developed in the 18th century and it has been so effective. It was used till only recently, when a new process called the contact process has replaced the lead chamber process to produce sulfuric acid. The two main chemicals that are added in the lead chamber process are nitrogen oxide and sulfur dioxide. Nitrogen oxide is added from the left, as you can see here, into this glower tower. So is sulfur dioxide. Nitrogen oxide and sulfur dioxide are both led into these three chambers shown in the middle, these brown chambers. These chambers are made of lead, which gives the whole process of preparation of sulfuric acid its name, the lead chamber process. Note that the lead is not in any way connected to the preparation of sulfuric acid. It just gives us cheap, inexpensive and yet very strong containers, and that is why we use lead chambers in this process. Now nitrogen oxide and sulfur dioxide are introduced into these chambers. Well, there these gases are heated. Now when they are heated, nitrogen oxide combines with oxygen to form the gas nitrogen dioxide. So all these three chambers soon form nitrogen dioxide gas. But water is being added and poured over these chambers. You can see that, isn't it? Since water is being poured, nitrogen dioxide gas dissolves in water to form nitrous acid and nitric acid. Understood? Nitrous acid is HNO2 and nitric acid is HNO3. These two acids are formed. Sulfur dioxide reacts with nitrous acid and a mixture of nitrous acid and nitric acid to form sulfuric acid. And there you go. That is how sulfuric acid is produced in this process. Understood? So first NO became converted to NO2, then NO2 reacted with water to form HNO2 and HNO3, and then sulfur dioxide, which is also present in these chambers, reacts with HNO2 and HNO3 to form sulfuric acid. When sulfur dioxide reacts with nitric acid and nitrous acid, it forms sulfuric acid, but it also releases NO and NO2 gases, and therefore nitrogen oxide and nitrogen dioxide act as catalysts in the lead chamber process. They are not completely used up. Understood? After all, they are released when sulfuric acid is formed. So basically sulfur dioxide is converted to sulfuric acid, while nitrogen oxide and nitrogen dioxide are catalysts in the process. The sulfuric acid produced, below the chamber here, it flows out of all these chambers, has a consistency of around 50%. There are, however, some gases also, which are present in these chambers which do not dissolve in water, isn't it? These gases are then taken back to the glower tower, like this arrow shows them being taken back to the glower tower. Similarly, some nitric acid and nitrous acid does not react with sulfur dioxide. That is also taken back to the glower tower. The purpose of the glower tower is to extract all the gases which have not been used and to send them for use yet again. Understood? That is the purpose of the glower tower. Some of the HNO2 and HNO3 which did not react in the chambers reacts with new incoming gases in the glower tower and forms some more sulfuric acid here, and this sulfuric acid has a concentration of around 60%. I know the process seems sort of complicated, but the crux of the process is what you need to understand. Sulfur dioxide gets oxidized to sulfuric acid. Nitrogen oxides act as a catalyst. So that's about the lead chamber process. Let's now take a look at the equations involved in the lead chamber process. So here are the equations involved. As I said, first nitrogen gets converted to nitrogen dioxide in the presence of oxygen. This nitrogen dioxide reacts with the water that is sprayed above the three chambers to form HNO2 and HNO3. HNO2 is nitrous acid and HNO3 is nitric acid. Now sulfur dioxide gas reacts with HNO2 to form sulfuric acid and nitric oxide, NO. Sulfur dioxide gas also reacts with nitric acid to form a compound called NOHSO4. NOHSO4 is nitrosyl sulfuric acid. It is a byproduct and it immediately reacts with HNO2 to form sulfuric acid, NO2 and NO. NO2 is nitrogen dioxide and NO is nitric oxide. So basically these two reactions occur. Sulfur dioxide reacts with only HNO2 and it also reacts with both HNO3 and HNO2 to form nitric oxide and nitrogen dioxide. And this is how sulfuric acid is produced. If you add up all of these equations, then this is the equation you will get. 2SO2 plus 2H2O plus O2 gives 2H2SO4. What this tells us is that nitrogen oxides are all catalysts in this reaction. Understood? Nitrogen dioxide is a catalyst. A catalyst is a substance that does not take part in a reaction, but it helps in the reaction. That's the case with nitrogen oxide and dioxide here. They help in the reaction, but they do not take part in the reaction. Understood? That is why when we add up all the reactions, they don't even figure in the equation. We get just SO2, H2O and O2 in the final equation. So there you go. This is about the lead chamber process. Here's a question related to the lead chamber process. This one here. Which of the following compounds is absolutely essential in the lead chamber process? A. Potassium, B. Nitrogen oxides, C. Platinum, or D. Lead? The answer is clearly nitrogen oxides. As we just discussed, it is nitrogen oxides which act as a catalyst in the lead chamber process. Platinum and potassium are not used at all, and lead is simply used to make the containers of the lead chambers. After all, lead is inexpensive and it doesn't react with acids. That is why lead is used. But otherwise, it does not take part in any reaction. So that's our answer. The next process that we'll talk about is the Ostwald's process. The Ostwald's process is the process of preparation of nitric acid, in the industry from ammonia and oxygen. Understood? That's what the Ostwald's process is. On your screen you can see a small animation that depicts the Ostwald's process. As you can see, there are 3 chambers in the Ostwald's process. The first one is called converter, the second one is called oxidation chamber, and the third one is called absorption tower. In the converter, ammonia and oxygen in the volume ratio 1:8 are fed in. So you must remember that the net raw materials in the Ostwald's process are ammonia and oxygen. These are gases. They are passed through a platinum gauge and they are heated to a temperature of 900 degrees Celsius at a pressure of 4 to 10 atmospheres. When that happens, ammonia reacts with oxygen to form nitric oxide, that is NO. Understood? This NO here. So NO gas flows out of this converter into the oxidation chamber. Platinum acts as a catalyst in the reaction between ammonia and oxygen. In fact, platinum is not the only catalyst. This platinum here also has 10% of a metal called rhodium in it. So platinum with 10% rhodium is the actual catalyst, for the reaction of ammonia and oxygen. And as I just said, the pressure must be 4 to 10 atmospheres with the temperature being 900 degrees Celsius. Now this nitric oxide formed enters the oxidation chamber and it gets converted into brown colored nitrogen dioxide gas. So nitrogen dioxide gas is formed in the oxidation chamber. This gas flows towards the right into the third chamber called the absorption tower. Now you can see that a shower of water is falling in the absorption tower. What this shower of water does is it dissolves the nitrogen dioxide inside it and forms nitric acid, because nitrogen dioxide dissolves in water or reacts with it to form nitric acid. This nitric acid flows down and it is removed from the bottom of this absorption tower. You can see a lot of quartz pieces here in the middle of this absorption tower. So why are there quartz pieces here? Quartz pieces are basically like sand grains, They basically serve the purpose of increasing the contact time and contact area between nitrogen dioxide and water. If there were no quartz pieces, water would just rush down immediately and it would get a few milliseconds or a few seconds, to react with nitrogen dioxide. But because there are quartz pieces, the nitrogen dioxide gas slowly rises up through the quartz pieces and the water slowly trickles down through the quartz pieces, and so proper interaction takes place between the nitrogen dioxide gas and water, and so a lot of nitric acid is produced. Understood? Any remaining gases are removed from the top part of the chamber through this waste gases pipe here. There you go. This is the crux of the Ostwald's process to produce nitric acid. Let us look at all the reactions that take place in the converter, the oxidation chamber and the absorption chamber right now. So here's the first equation in the Ostwald's process. As I said, ammonia first reacts with oxygen to form nitric oxide and water. This nitric oxide then passes into the oxidation chamber where this reaction occurs. NO plus O2 gives NO2. Then this nitrogen dioxide reacts with water from the shower in the absorption tower to form 2HNO3 and NO, that is nitric acid and nitric oxide gas. This nitric oxide gas formed is then removed from this chamber and sometimes reused and reintroduced in the oxidation chamber for this reaction, the second one. So that's how the Ostwald's process works. Ammonia and oxygen react to eventually form nitric acid. That brings us to the end of this chapter. The chapter in which we learnt about so many compounds and so many processes. Let's move on to the next one.